we built the most advanced eye in human history, a $10 billion time machine, operating at minus 233 degrees Celsius. But this machine didn't show us how well we understand the universe. It showed us that we actually know nothing. When Webb's flawless data began to flow, all our models collapsed. Because, in a period when the universe was only 3% of its current age, it found galaxies as massive as today's Milky Way. These galaxy breakers seem to have turned 100% of available matter into stars. This was mathematically impossible. Furthermore, it measured the expansion rate of the universe and confirmed two conflicting numbers, 67 and 73. This meant physics was in a fundamental crisis. But the real issue was that this picture was only the tip of the iceberg. If the fact that science's greatest achievement led to its greatest mystery is an irony to you, then join this journey. Because the secrets this machine whispers will make you question reality itself. We are beginning. For years, we thought we knew the boundaries of the universe. Generations of astronomers believed they were mapping space within a measurable bubble with a radius of 14 billion light-years. But that assumption shattered suddenly when the James Webb Space Telescope turned its cold, dark gaze toward the void. Because in those dark regions we thought were empty, Webb found a complex history, not nothingness, galaxies formed with impossible speed, and black holes growing much faster than our models allowed, appeared from the shadows. Now, we know that what we see is not the whole of reality. It is only a tiny piece. To understand this massive discovery, we must set aside our most basic assumption, the act of seeing. In daily life, seeing is instantaneous. Light crosses a room so fast that your brain perceives it as the present. But the universe does not work on a human scale. Light moves at a constant and massive speed of 300,000 kilometers per second. Although this speed seems like a universal limit, when distances reach cosmic scales, even light becomes a slow factor. Because when you look at an object, you do not see it as it is. You see it as it was, the moment light left it. When looking at the moon, you see its past from 1.3 seconds ago. When looking at the sun, you observe its past from 8 minutes ago. If the sun disappeared right now, the sky would continue to shine for 8 minutes, as if nothing had happened. Therefore, the night sky is not a live broadcast. It is a giant recording. Distance separates not just objects, but time. Looking into the depths of space is more like boarding a time machine than using a telescope. Because every single photon is an ancient messenger, surviving through space, carrying a memory from billions of years ago. So, what does this time travel tell us about the beginning of the universe? This is where the real problem starts. Because these messengers transform along the way. Because the universe is expanding. This does not mean galaxies are flying here and there in a void. It means the space between galaxies is stretching. For billions of years, this silent expansion changes everything traveling through space, including light. As space stretches, the wavelengths of light also stretch, just like a rubber band. Energetic blue and violet light shifts first to red and then into the invisible infrared. This phenomenon, known as redshift, is not an optical illusion. It is a physical measurement of how much the universe has expanded during its existence. The further the light comes from, the more its wavelength has stretched, and the more it comes from an ancient era of cosmic history. Legendary telescopes like Hubble focused mostly on visible light. Therefore, the early ages of the universe looked dark and empty to them. But that place was not empty. It was just invisible. This is exactly why James Webb was designed differently. With its gold-plated mirrors and massive sun shield, it cools itself down to -233 degrees Celsius. Webb virtually disappears thermally, just to hear the oldest, faintest infrared whispers of the universe. In this way, it opens the doors to that invisible universe that Hubble could not see. However, when Webb looked into this darkness, it did not find the silence predicted by theories. On the contrary, it encountered an impossible crowd. Scientists imagined the beginning of the universe, like a slow awakening after the Dark Ages. In the first few 100 million years after the Big Bang, galaxies were expected to be small, faint, and scattered. It should have taken hundreds of millions of years for gas to cool, for gravity to accumulate matter, and for stars to form. This was like a cosmic construction project. First, the foundations, then the skyscrapers. But when Webb's data arrived, these models were leveled to the ground. The telescope looked at a period equivalent to only 1% of the universe's current age. While expecting to find weak galaxies, it discovered surprisingly bright, massive, and well-structured systems. Some of these galaxies had stars totaling hundreds of millions, or even billions of solar masses. This was much more than what should have existed at that time. These systems were not barely surviving. They were producing stars at an incredible rate. Even stranger, the spectra of these supposedly primitive galaxies carried signatures of carbon and oxygen. These elements do not come from the Big Bang. They are forged in the hearts of stars. This means that while the universe was still a baby, a generation of stars had already been born, lived, and died. This was like a newborn baby receiving a university degree immediately after birth. The universe had grown much faster than we thought possible. This situation created a shockwave that astronomers called the too early, too much light crisis. But this unthinkable speed was not limited to stars, because even bigger monsters were growing in the heart of the darkness. Supermassive black holes, ahachi, nested at the center of galaxies, deepen this mystery even further. According to standard models, it takes time for a black hole to grow, because matter falling into it heats up and emits radiation. This radiation pushes away additional matter, applying a natural speed limit. But Webb detected monsters with masses reaching millions, or even billions of times that of the Sun, when the universe was younger than 500 million years. These black holes seemed to not care about these physical speed limits at all. Either massive gas clouds bypassed the star phase and collapsed directly, forming direct collapse black holes, or the first stars were much more massive than those we know today, and left behind giant seeds after collapsing. Whatever the reason, the result was dizzying. The beginning of the universe was not a calm dawn. Yes, it was a violent, noisy, fast, and efficient explosion. matter and gravity performed a much more aggressive dance than we imagined. These early structures compress the cosmic history calendar and force us to question our most basic assumptions. Because the formation of such large structures in such a short time shows that the density and distribution of matter at that time was very different from what we thought. Webb is not just filling in the missing pieces. It is showing us that we are holding the picture upside down. The speed of light, redshift, and this unexplained early maturity of the universe, molnritir, change everything we thought we knew about the scale of the cosmos. If the universe is this rich, complex, and structured right at the edge of our vision, then what might be hidden in that giant ocean beyond the border, where light will never reach us? Because James Webb did not show us an end. It showed us a door opening to infinity. But to pass through this door, we must first understand how crowded the universe actually is. Because those dark regions we thought were empty are actually like a giant metropolis, where trillions of galaxies hidden by time reside. Webb's eyes, scanning the depths, revealed an ocean of galaxies, reaching back to the very beginning of cosmic history, overlapping and masking each other's light. This discovery is not a simple numerical correction. It is a complete rewriting of our perception of cosmic density, impossibly, because those places we thought were empty were actually the most crowded neighborhoods of the universe. Our eyes were just not advanced enough to see them. To understand this crowd, we must return to that simple but giant question astronomers have chased for years. How many galaxies are there in the universe? When the Hubble Space Telescope did this, it found thousands of galaxies in a tiny area, the size of a grain of sand. When this ratio was applied to the entire sky, it appeared there were a few 100 billion galaxies in the universe. But when James Webb looked at the same darkness, the situation changed. Webb, collecting infrared light that Hubble could not see, peeled back the layers behind those voids. Areas that previously appeared dark were suddenly filled with hundreds of thousands of faint, dusty, and extremely old structures. This new census raised the total number of galaxies in the universe from hundreds of billions to trillions. This is a terrifying number, because trillions of galaxies mean trillions times billions of stars, planets, and possibilities. But the most shocking part was realizing that this crowd was not randomly distributed. These trillions of galaxies are not drifting aimlessly in space. There is an invisible skeleton that holds, shapes, and directs them. We call it the cosmic web. Webb's data clearly showed that galaxies are lined up along giant filaments, tens of millions of light years long. At the intersection points of these filaments, giant galaxy clusters form. Between them, massive and eerie voids stretch out. This structure resembles a spider web. Matter exists only on the strands. The rest is a dark nothingness. However, the architect of this web is not the stars or gas clouds we can see. The power that built this massive structure is dark matter, which makes up 85% of the universe, but which we can never see. Dark matter does not reflect, emit, or absorb light. We feel its existence only through gravity. It is the invisible scaffolding of the universe. Webb revealed how quickly galaxies in the early universe came together on these dark matter filaments, huddling as if following an invisible highway. All these concepts, invisible scaffolds, expansion exceeding the speed of light, hidden trillions of worlds, and photons racing against time, have set the stage. Now, we know that the universe is not just big, but also a living, dynamic, and violent place. To understand why our models collapsed and why what we called impossible is possible, it is time to look at the actors, not the stage, because every time the Webb telescope looked into that deep darkness, it did not just see a general structure. In every frame, it found individual, shocking objects that made astronomers jump out of their seats and say, "This should not be here." So, what exactly were these concrete discoveries that threw theories into the trash? And how did they change the future that awaits us? And at that moment, when the data hit the analysis screens, a quiet but deep shockwave spread through the scientific world. The images Webb sent were not a theoretical correction or a minor update. They were like boiling water poured over the baby photo of the universe. The things we saw were not just a little bigger or a little brighter. There, in the deepest point of the darkness, stood monsters that the laws of physics should never have allowed to exist at that age. The first and biggest shock came with the galaxies that appeared just 300 to 500 million years after the Big Bang. According to standard cosmological models, the universe should have just been waking up in that era. At best, there should have been faint, scattered, and shapeless gas clouds. But James Webb found full-fledged galaxy cities there, with spiral arms and incredible brightness. These systems had hundreds of millions, and some billions of solar masses worth of stars. Under normal conditions, it takes billions of years for gravity to bring so much matter together and organize it. Yet, these galaxies were there, in a slice of only 3% of the universe's current age, as if they had bent time itself. This discovery was so abnormal that scientists initially thought the data was faulty. Because, according to calculations, even turning 100% of all the gas at that time into stars could not explain this brightness. But the data was correct. And deep field surveys like JADE's proved that these impossible galaxies were not an isolated anomaly. They were popping up in every corner of the universe like mushrooms. This was like finding university professors in a kindergarten classroom. The universe had grown much faster than we thought possible. And this discovery invalidated galaxy formation theories overnight. But the real horror was hidden, not just in the appearance of these galaxies, but in their hearts. Webb detected supermassive black holes sitting at the center of galaxies, even before the universe had reached 500 million years of age. These were not the expected small, stellar black holes. No, these were giants with masses of millions, or in some cases, 1 billion times that of the Sun. The laws of physics categorically said stop to this. Because when a black hole swallows matter, that matter overheats and emits massive radiation. This radiation pressure pushes back newly falling matter, slowing its feeding. This is called the Eddington limit. And this limit puts a natural and insurmountable brake on a black hole's growth speed. According to this mathematical limit, it would take billions of years of continuous feeding for a black hole to reach this size. Yet, the time required for the formation of these monsters, Webb found it was even longer than the total age of the universe at that moment. Because this was as impossible as a 3-month-old baby having eaten as much as an adult. Therefore, astronomers are now forced to discuss exotic and eerie scenarios. Perhaps these black holes did not form from stars. Perhaps giant gas clouds collapsed directly, without ever becoming stars, forming direct collapse black holes. This idea was a fantasy on paper for years, but Webb turned it into a terrifying possibility. And as if these structural and gravitational anomalies were not enough, Webb also revealed a chemical impossibility. Well, in the first lights of the universe, there should have been only hydrogen and helium left over from the Big Bang. All other elements, like the carbon that makes up life, the oxygen we breathe, and the nitrogen in our DNA, should have been produced inside stars. But when Webb looked at the spectra of these first galaxies, it found surprisingly strong signatures of carbon and oxygen. These elements cannot exist spontaneously in the vacuum of space. They must cook for millions of years in the cores of stars. Those stars must die, explode, and scatter these elements into space. Then, new stars must be born from these ashes. This cycle takes time. It requires generations of stellar death. Yet, Webb found a metal abundance, carrying the signature of 3rd or 4th generation stars, while the universe was still taking its first steps. This was like hundreds of pages being torn out from the beginning of the universe's history book. It was as if someone had turned the cosmic clock forward. Chemistry had paved the way for biology. Much earlier than we thought, the final blow came with scale. That massive cosmic architecture. Webb imaged giant galaxy filaments and chains, tens of millions of light years long, in the early universe. It was not expected for the cosmic web to be so organized in such an early era. Gravity is a patient architect. It lays bricks slowly and raises structures slowly. But here, in the first moments of the universe, it was as if a giant scaffolding had already been set up. Galaxies were lined up like beads on a string, and already clustered. Even in the most advanced supercomputer simulations, the formation of these structures takes billions of years. Webb found them, in the universe's infancy, fully formed. Oversized galaxies, black holes growing at impossible speeds, timeless elements, and early formed giant structures. These 4 discoveries are shaking the foundations of modern cosmology. The data was stubborn, and it grew stronger with every new observation. The universe had made a much faster, much more violent, and much more efficient start than we thought. This situation has brought scientists to the edge of an eerie, but equally exciting abyss. If known physics, the Standard Model, and the laws of gravity cannot explain how these structures formed, then is there another hand guiding the universe? And could the fingerprints of this secret hand be hidden in the expansion rate of the universe, in modern physics' greatest crisis? And when Webb was launched to solve this mystery, the scientific world held its breath. The telescope was supposed to end this debate, clarify the numbers, and write the final chapter of the cosmology book. However, the telescope did not give us an ultimate answer. It gave us a much bigger question mark that hit our existing models like a slap. Because Webb's precise observations showed that everything we thought we knew about the universe's expansion rate, yes, how, might be fundamentally wrong. This crisis is called the Hubble Tension. Scientists use two different methods to measure the expansion rate of the universe, and these methods offer two different, non-compatible realities. The first method looks at the cosmic microwave background radiation, the baby photo of the universe. This method measures the expansion rate with extraordinary precision at 67 kilometers per second per megaparsec. This is the prediction of the Standard Model and one of the most reliable strongholds of physics. But the second method looks at the modern universe, at nearby supernovae and Cepheid variable stars. This method stubbornly gives a higher number, 73 kilometers. For years, astronomers thought this difference was a measurement error. Perhaps the Hubble telescope was aging. Perhaps dust clouds were affecting the brightness of stars. When Webb was launched, everyone hoped its superior resolution would correct this error and pull the 73 figure down to 67. However, when Webb turned its piercing and cold gaze toward the Cepheid stars, it did not correct the error. It confirmed the error. The telescope proved that the measurements were flawless, that dust was accounted for, and that the local part of the universe is indeed expanding 9% faster than expected. Much faster. This result is terrifying, because if both methods are correct, then what is wrong is not our measurements, but our way of understanding the universe. But Webb's shocking revelations were not limited to speed. They also revealed a staggering truth about the density of the universe. Deep field images showed that the number of galaxies in the universe did not just exceed our estimates, it crushed them. For years, we assumed there were about 200 billion galaxies in the universe. Even this number was massive for the human mind. However, when Webb focused on the darkest, emptiest looking points in the sky, it found not darkness, but a wall of overlapping light. Regions that Hubble previously recorded as voids were filled with hundreds of thousands of faint, dusty, and old galaxies in Webb's infrared eyes. This new census took the total number of galaxies in the universe to the trillions. 1 trillion galaxies, each home to billions of stars, trillions of planets, and infinite possibilities. This means the universe is at least 10 times more crowded than we thought. But the most disturbing part of this discovery is not the size of the number, but what this crowd means. If even the visible part of the universe is this packed, then what a small piece of reality is this sphere 93 billion light-years in diameter that we call the observable universe? Webb is perhaps showing us only a single drop in an ocean, and even the inside of that drop is full of a cycle of life and matter that stretches the limits of our imagination. And despite all this crowd, all this speed, perhaps the discovery that triggered Webb's most existential crisis was about the future of the universe and the absolute dominance of dark energy. When the telescope analyzed the light of the most distant galaxies, it confirmed once again that they are not just moving away from us, they are escaping by accelerating. This mysterious energy, which makes up 70% of the universe, is constantly stretching the fabric of space-time. Normally, gravity would be expected to slow this expansion. But the opposite is happening. Webb's data whispers that this expansion is an irreversible process, and that the ultimate fate of the universe will be great loneliness. This situation means that the cosmic horizon works like a ruthless eraser. The speed of light is constant, but at very large distances, the expansion rate of space exceeds the speed of light. This means that those giant galaxies we see with Webb right now, those trillions of worlds, are slowly breaking away from us, from our cause and effect relationship. For future observers, the sky will not be as rich as it is today. Galaxies will pass behind the event horizon one by one, and their light will never reach Earth again. The universe is erasing itself. The Hubble Tension, hidden trillions of galaxies, and a universe tearing itself apart by accelerating. When these three discoveries combine, the resulting picture is not the calm, predictable universe model of the 20th century. We are facing a wild reality that bends rules, destroys itself, and is much larger than we can perceive. In the midst of all this cosmic chaos, a much more technical, much more concrete question sticks in our minds. How can a man-made machine, a mechanism of cold metal and mirrors, see the beginning of time? How can it catch those faint heat waves, floating in space for billions of years, like noticing a candle flame in the middle of a storm? Now, it is time to look at that engineering marvel that made these impossible discoveries possible. How does the greatest eye of humanity work? But how does it work? How does it work? The fact that the human mind can get this close to the beginning of time cannot be explained by luck or a simple lens. Because Webb is not just an ordinary telescope launched into the sky. It is a time machine designed to operate in the most hostile conditions of space. In absolute cold Taoriu, where every single part is designed to achieve the impossible. The secret of its success lies not just in its size, but in how it manipulates light, how it defeats heat, and how it turns the weakest signals of the universe into a magnificent symphony. Now, it is time to look under the hood of this engineering miracle and dive into the details of the technical genius that made those shocking discoveries possible. Let's start with Webb's most basic ability, the power to see the invisible. Legendary telescopes like Hubble were essentially designed to capture visible light, the wavelengths the human eye can perceive. However, in the depths of the universe, visible light hits a wall. As space expands, light waves that have traveled for billions of years stretch, lose their energy, and shift to the red end of the spectrum, and then to the infrared. This means that the first galaxies of the universe were invisible to Hubble. Even if they were there, their light had moved out of the range Hubble could see. Webb was built as an infrared eye, specifically to solve this problem. Just as night vision goggles detect warm objects hidden in the dark, through their thermal radiation, Webb catches those old and faint galaxies, hidden behind the cold dust clouds of the universe, in infrared wavelengths. While Hubble can see near-infrared light between 0.8 and 2.5 microns, Webb pushes this limit to 28 microns, deep into the mid-infrared. This does not just mean seeing a little further. It means seeing behind walls. Because infrared light can pass through the cosmic dust clouds that block visible light. almost without being affected. Therefore, Webb can observe the most intimate moments of the universe, stellar nurseries and galactic cores. Where Hubble sees a dark mist, Webb sees glowing stars and rotating gas disks. But capturing infrared light brings a deadly problem: heat. Infrared light is essentially thermal radiation. Everything that is warm, like the Earth, the Sun, or even the telescope itself, emits infrared light. If Webb were a device operating at room temperature, the glow of its own heat would completely blind the faint signals coming from the depths of the universe. This is like trying to see the stars at noon, while the sun is overhead. For Webb to see these faint glows, it must be thermally dead. This is where the most elegant and massive engineering solution comes in: the sun shield. This shield is a structure roughly 21 meters by 14 meters, the size of a tennis court, in the shape of a 5-layered kite. Each layer is thinner than a human hair, made of a special polymer called capton, coated with aluminum and silicon to reflect heat. These 5 layers do not touch each other. There is a gap between them. This gap allows heat to dissipate into space between the layers. The outermost layer faces the sun, and its surface heats up to 85 degrees Celsius. However, on the innermost 5th layer facing the telescope, the temperature drops to minus 233 degrees Celsius, only 40 degrees above absolute zero. This means creating a temperature difference of more than 300 degrees in a single structure. On the hot side of the shield, water could boil. On the cold side, nitrogen would freeze. Thanks to this thermal insulation, Webb swallows its own heat like a black hole, allowing its detectors to hear even the weakest signals of the universe. If this shield had not existed, or if it had torn during launch, the $10 billion telescope would have turned into a blind and useless heap of metal, drifting in space. This mechanism is not just a protection. It is Webb's reason for being. Seeing and cooling is not enough. You also need to collect that light. The power of a telescope lies not in its magnification, but in its light-collecting capacity, meaning the size of its mirror. The larger the mirror, the fainter the objects it can see, and the finer the details it can resolve. Hubble's mirror was 2.4 meters in diameter and was a single piece of glass. But for Webb's goals, this size was not enough. A mirror of at least 6.5 meters was required. The problem was that no rocket could carry a single-piece mirror 6.5 meters in diameter into space. Rocket cargo bays are narrow, and fitting such a wide load was physically impossible. Engineers solved this problem by making the mirror foldable like origami. Webb's mirror is not a single piece. It consists of 18 hexagonal segments. Each segment is 1.32 meters in diameter and is made of a special metal called beryllium, which is stronger than steel, but lighter than aluminum. Beryllium is one of the rare substances that can maintain its shape in extreme cold temperatures. During launch, these mirrors were folded, tucked into the rocket, and in space, without human intervention, they opened with a precision of 1/millionth of a millimeter to form a single giant mirror. Another critical advantage of this segmented design is the tiny motors located behind each mirror. These actuators can adjust the tilt and position of the mirrors on a nanometer scale. while Hubble's collecting surface was about 4.5 square meters. Webb's giant honeycomb structure offers a light collecting area of 25 square meters. This means Webb can collect about 6 times more light than Hubble and can obtain an image in a much shorter time than it would take Hubble. But collecting and focusing light is only half the job. For this light to mean anything, there is a need for brains to analyze it, break it down into its components, and convert it into digital data. Behind Webb, at the focal point of the mirror, are 4 main scientific instruments that constitute the telescope's true power. The first, and perhaps the most famous, is NIRCam, the near-infrared camera. It is the main imager that takes those breathtaking, high-resolution photos of Webb. But NIRCam does not just take beautiful photos. It is also an ultra-sensitive sensor designed to catch the oldest light in the universe. NIRCam detects wavelengths between 0.6 and 5 microns. This is the range where the light of the first stars and galaxies has shifted due to universal expansion. Inside the instrument, dichroic beam splitters split the light into different colors. This allows NIRCam to observe at different wavelengths simultaneously. Special coronagraph masks physically block the light of a bright star, making faint planets orbiting around it visible, just as you cover the sun with your hand to see the surroundings. Infrared vision, a massive sunshield, a foldable honeycomb mirror, and NIRCam's sensitive eyes. These transform Webb into the most complex and powerful observation tool in human history. But Webb's capabilities do not end here, because seeing the light is not enough. It is necessary to read its chemical fingerprint and decipher the elements, temperature, and movement within it. This is where the other instruments come in, doing much more than taking photos, deciphering the chemistry of light. So, how can these other detectors, measuring water vapor in a planet's atmosphere or the speed of a galaxy, extract so much detail from those faint points of light? And to solve this hidden chemistry, Webb must act not like a photographer, but like a cosmic detective. Capturing an image of an object tells you where it is, but it does not tell you what it is made of, how hot it is, and how fast it moves. This is where spectroscopy comes in, which splits light into rainbow colors, its spectrum. This process is like reading the barcode of the universe. When you look at the outside of a soup can in a supermarket, you only see its brand. Rainbow says quartz, but when you scan its barcode, you learn its ingredients, production site, and price. Webb's NNIR spec instrument, the near-infrared spectrograph, is exactly this scanner that reads the barcode of galaxies billions of light years away. Because the working principle of NIRSpec is based on splitting light into its components by passing it through a prism. However, the problem Webb faced was that the sky is very crowded. Old telescopes like Hubble could only take the spectrum of one or a few objects at a time. This was a very slow and inefficient process, like examining every single straw while looking for a needle in a haystack. Webb needed to analyze thousands of galaxies quickly. Engineers developed one of the most complex micromechanical systems in human history to solve this problem: the microshutter array. This system consists of approximately 250,000 tiny windows, placed on a silicon plate the size of a postage stamp. Each window is thinner than a human hair and can open and close independently. This gives Webb the ability to choose which star or galaxy light to let in and which to block while looking at the sky. A magnetic arm scans these windows and opens the shutters over the targets determined by scientists, while keeping others closed. In this way, Webb can block the light of bright and disturbing stars in the foreground, focusing on faint background galaxies, HARS, right behind or next to them. It can take the spectrum of more than 100 different objects in a single exposure. This technology increases the speed and efficiency of observations, hundreds of times compared to old methods. Without NIR spec, it would have taken Webb decades to characterize and verify the ages of those thousands of early universe galaxies mentioned in the second chapter. These micro windows allow the oldest secrets of the universe to be whispered, not one by one, but collectively. However, NIRCam and NIRSpec focus on the near part of infrared light, between 0.6 and 5 microns. To see the colder, older, and dustier regions of the universe, it is necessary to go deeper into the mid-infrared region. This is where Webb's coldest heart, MIRI, the mid-infrared instrument, comes in. MIRI sees wavelengths between 5 and 28 microns. This region is of critical importance because water vapor in planet-forming disks, hydrocarbons, and supermassive black holes hidden behind dust in galaxy centers emit their strongest radiation in this range. We can compare MIRI to a thermal X-ray machine. Just as a doctor looks under the skin with an X-ray and sees the bones, MIRI penetrates into dense dust clouds and sees newborn stars or hidden planets. For MIRI to work, it must be much colder than other parts of Webb. Mid-infrared light is extremely sensitive to heat. Webb's sun shield cools the telescope to minus 233 degrees Celsius, which is sufficient for NIRCam. But T6 for MIRI. This temperature is as hot as a tropical summer day. For MIRI to suppress the heat emitted by its own detectors, called dark current, it must operate at minus 266 degrees Celsius, only 7 degrees above absolute zero. Reaching such a low temperature with passive cooling, just by standing in the shade, is physically impossible. Therefore, engineers placed a giant and complex refrigerator inside Webb, the cryocooler. This system draws heat from MIRI and throws it into space by circulating helium gas in a closed loop. Whilst old generation infrared telescopes carried limited amounts of liquid helium tanks. When the coolant ran out, the telescope would heat up and die. But Webb's cryocooler does not consume fuel. It cools continuously by mechanically compressing and expanding the helium. This system is designed to be stable enough to ensure that the vibrations it creates while working do not disturb Webb's delicate images. Thanks to MIRI, Webb does not just say, "There is something there." It can say, "There are organic molecules there. There is water there. There are the building blocks of life there." Without this active cooling system, Webb could not see half of the universe's chemical history, the final and most critical component. Required for all these sensitive optics, micro windows, and coolers to work is stability. While Webb floats at the L2 Lagrange point, 1.5 million kilometers from Earth, it must lock onto a star for hours, sometimes days. This is like trying to point a laser at a coin miles away from a moving train without shaking at all. Even the slightest tremor, a micron-level shift, ruins that long exposure and turns the image into a blurry smudge. The hero that accomplishes this task is the FGS, the Fine Guidance Sensor. Cartier's FGS is a digital anchor that checks where the telescope is looking 16 times per second during a scientific observation. It selects a specific guide star in the sky and constantly updates the telescope's position relative to this star. If the telescope deviates even a millionth of a millimeter, FGS detects this and immediately corrects the image by sending a signal to the fine steering mirror. This system is so sensitive that it can detect a person blinking in Los Angeles while looking from New York. This stability is vital, not just for clear photos, but also for examining the atmospheres of exoplanets. When a planet passes in front of its star, it causes a 1 in a million drop in the star's light. For Webb to measure this tiny change and how starlight changes as it passes through the planetary atmosphere, the telescope must be in absolute stability. FGS and its companion, NIRISS, watch these transits to search for water, methane, carbon dioxide, and even potential biological signatures in the air of distant worlds. Infrared vision, a giant foldable mirror, thermal shield, micro shutters, cryocooler, and a nanometer-scale guidance system. Each of these mechanisms, representing the peak of engineering, works in perfect harmony inside Webb. The machine has far exceeded designs on paper, displaying a performance better, clearer, and deeper than expected. Technically, Webb is the most perfect, sensitive, and powerful observation tool humanity has ever produced. But what is as exciting as it is eerie is that the results this perfect machine shows us definitely do not match the orderly and understandable universe picture we expected. The tool works perfectly, which means the impossible data it sees is not an error, but reality itself. The telescope screams to us that while we thought we had solved the mechanics of the universe, we actually missed the most basic gears. Because when the data collected by this technical wonder are combined, the big picture that emerges points to a breathtaking climax concerning not just astronomy, but our cosmic fate and the ultimate end of our existence. So, what is at the end of this big and scary story Webb tells us? When all these pieces are combined, and now, beyond technical details and cold metal, the curtain of the true miracle is opening. Because Webb was not just a better telescope, it was a messenger, revealing our deepest secrets, our darkest fears, and our greatest hopes. Because when those spectra and images combine, what emerges is not just a series of astronomical data, but a cosmic revolution. While the scientific world expected minor corrections, Webb flipped the table. Now, fasten your seatbelts, because the things you will see are not theoretical, they are real. And these realities did not just update the history book of the universe. It burned it and wrote a brand new, much wilder story from its ashes. The first blow came from a ghost that redrew the boundaries of the universe. JADES-GS-Z-13-0. This might sound like a technical code to you, but for astronomers, this is a shockwave. When Webb found this galaxy, shining only 320 million years after the Big Bang, a silence fell over the world of cosmology. Because at that time, it was impossible for the universe to produce something this bright. JADES-G S-Z 13-0 was not just old. It was an anomaly that pushed the boundaries of time. We were looking back 13.4 billion years. This was an infancy period, equivalent to only 2% of the universe's current age. But this galaxy, which should have been a baby, was not a faint candle flame. It was shining like a spotlight. The star formation rate was incredible. Every year, it produced new stars totaling 5 to 10 times the mass of the Sun. This was way above the speed at which gas could cool and collapse at that time, according to theoretical models. Even worse was the mass of this galaxy. It had a stellar population equivalent to hundreds of millions of solar masses. This was like a 3-month-old baby running a marathon. According to the laws of physics, enough time had not passed for gravity to turn such scattered gas clouds into such an organized structure in such a short time. Foggy, but Webb was not wrong. Spectroscopic analyses confirmed the redshift value was ZE equals 13.2. This was not a record. It was a challenge. And scientists began publishing articles with titles like The Impossible Galaxy, because JADES-GS-Z 13-0 was not alone. It was only the first warning, transparent. Webb showed that this process was not homogeneous, but occurred in the form of giant ionized bubbles. Each of these bubbles was millions of light years in diameter. At their centers were hyper-bright galaxies, like jades and Loeb's monsters. These galaxies were emitting such strong ultraviolet radiation that they were carving out the space around them, dispersing the mist, and creating giant voids where light could roam freely. Webb watched the process of the universe becoming transparent, the transition from darkness to light, life. This was not just an observation. It was the movie of the universe's awakening. It was proof of how the first lights tore the darkness, how the fabric of the universe changed, and how today's bright universe was born. Jade's impossible age, the early existence of carbon dust, the universe-breaking Loeb monsters, the hungry black holes exceeding the Eddington limit, and the giant ionization, bubbles piercing the cosmic mist. These 5 epic pieces of evidence are the reality itself Webb offers us. But at the end of all these discoveries, all the collapsed theories, and all the rewritten histories, one final question remains that stretches our minds, makes us uncomfortable, and that we are afraid to answer. And that ultimate question is this: if even the visible part of the universe is this full, this wild, and this impossible, then what is really happening in that 95% dark part that we cannot see and will never see? This question is not just a scientific curiosity. It is a cosmic horror, because that wildly full and fast universe Webb showed us is actually only the visible, tiny, and bright part of the iceberg. That 95% dark region, dark energy and dark matter are the true masters of the universe. And their game plan is far beyond our imagination, much more dramatic, and much more ruthless. The things we see now are just a few bubbles floating on that giant dark ocean. The real story is being written in those invisible depths, where the silent war between gravity and expansion is fought. And Webb presents us with the most striking frontline reports of this war. The 6th epic blow came from that mysterious force that determines the fate of the universe. The possibility that dark energy is evolving. For years, we thought of dark energy as a cosmological constant. That is, an energy density that is equally distributed in every square centimeter of space, does not change with time, and is boring and fixed. But Webb's precise measurements on distant supernova and early galaxies whisper that this constancy might be an illusion. Some inconsistencies in the data point to the possibility that dark energy is a dynamic field whose power changes with time, something that evolves. This idea shakes cosmology to its foundations. Because if dark energy is not constant, all the scenarios we have drawn for the future of the universe could be trash. If its power is increasing, we might encounter a scenario called the Big Rip. In this scenario, the expansion accelerates so much that it tears apart first galaxy clusters, then galaxies, then stars and planets, and finally, even atoms. Everything breaks apart. If its power is decreasing, or if it turns negative one day, the universe could stop expanding and start collapsing in on itself. This is the Big Crunch scenario. Webb's data does not give a definitive answer yet. Second, but for the first time, it moved the idea out of dark energy's variability from speculation to the field of testable science. The fate of the universe is no longer condemned to a single possibility. 3 different scenarios are on the table. And we, like an audience who does not know the end of a movie, are waiting with bated breath. This is the greatest thriller of existence, and Webb showed us that the lead actor's character can change. But this is not the only movie Webb is showing us. The 7th blow came from the stories of other worlds, the chemical analysis of exoplanet atmospheres. For years, we could only detect exoplanets as mere points. We knew they existed, but we had no idea what kind of places they were. Webb, however, turned these points into habitable, and maybe even living worlds. For the first time in history, it detected carbon dioxide directly in the atmosphere of an exoplanet, in the air of this hot Jupiter called W-Sequoiasp 39. B, the existence of this gas, acet, which is a byproduct of life, was proven. This was not evidence of life, but it was evidence of ability. It showed that Webb could smell the atmosphere of a world like hundreds of light years away. Then, it went even further. It found possible traces of dimethyl sulfide, DMSADS molecules in the atmosphere of K2-18 EAB, a planet in the habitable zone. On Earth, DMS is produced almost entirely by marine life like phytoplankton. This discovery created a storm in the scientific world, because this was the first potential detection of a biological signature, a chemical that might have been produced by life. Of course, this is not proof, yet just a clue. But even this clue has the potential to answer the greatest question in human history. Are we alone? Webb could be the first tool, sectors, that can find the answer to this question, by looking not just at distant galaxies, but at worlds around neighboring stars. Now, we are not just asking, are there planets there? Now, we are asking, are there oceans on those planets? Is there air? And is there a trace of something breathing like us in that air? Webb moved these questions from science fiction to a part of observational astronomy. And the 8th blow, perhaps the most poetic one, came from the moments of birth and death of stars. In an irresistible beauty, At Webb-imaged stellar nurseries, iconic structures like the pillars of creation, which were previously hidden behind dust clouds with a clarity never seen before. The opaque dark pillars Hubble saw became transparent in Webb's infrared eye. It revealed hundreds of newly born, red-colored stars glowing inside them. These were baby stars, just emerging from their cocoons of gas and dust. We were seeing this moment, hidden for millions of years, for the first time. This was not just an aesthetic victory. This was a flood of data that fundamentally changed our star formation theories. We are examining at an atomic level how gas collapses to form stars, and how the jets emitted by young stars shape the surrounding clouds. But Webb recorded deaths, not just births. It observed the dying star at the center of the Southern Ring Nebula. When Hubble looked there, it saw only a single star, but Webb revealed that this star was actually a dying binary system. And the second, fainter star was hidden behind dust clouds. This completely changed our understanding of how the colorful gas layers a star emits while taking its last breath are formed. Because these complex and beautiful structures were created by the final dance of a dying pair, not a single star. Webb showed us that the universe is not just made of cold physics and mathematics. It is also a giant cosmic stage, where dramatic births, tragic deaths, and complex relationships take place. All these epic moments, impossible galaxies, universe-breaking monsters, changing fate scenarios, whispers of living worlds, and the final dances of stars. When these come together, the story Webb tells us is not just a list of scientific discoveries. It is the redefinition of our own existence. The universe is faster than we thought, more crowded, wilder, and maybe more alive. But now, in the middle of this dizzying speed and epic shocks, it is time to stop and breathe for a moment. Time to stop and think. Because the greatest question is still hanging in the air. Does all this massive scale, these unthinkable discoveries, this cosmic drama, really have a meaning for us, the small and temporary beings on this pale blue dot? And this question brings us to the final and deepest stage of our journey. And this question brings us to the final and deepest stage of our journey. Now, in the middle of this dizzying speed and epic shocks, it is time to stop and breathe for a moment. Time to stop and think. Because the greatest question is still hanging in the air. Does all this massive scale, these unthinkable discoveries, this cosmic drama, really have a meaning for us, the small and temporary beings on this pale blue dot? This is the true philosophical gift Webb offers us. The telescope is not just changing data, it is changing our perspective. Now, we feel ourselves not at the center of the universe, but in its heart. But this philosophical journey is not over yet. Sakat Sandur, because Webb's mirror reflects not just the past and the present, but also that frightening and inevitable future. In this stage of our journey, we face the first and most basic contrast: bigness and smallness. On one hand, there is a universe of unthinkable size, which Webb showed us, where even the observable sphere, 93 billion light-years in diameter, is just a drop, filled with trillions of galaxies, an ocean that seems infinite. On the other hand, there is you. With your height of about 1.7 meters, you are a being that is barely visible on this giant cosmic stage. almost zero in size. How can these two realities exist together? How is it that we exist as such a small piece, inside something so massive? This thought might initially create a feeling of deep insignificance, because, in the face of the universe's size, all our achievements, all our wars, and all our joys do not even take up as much space as a grain of sand. Physically, the probability of us reaching any of those trillions of worlds is zero. We will never walk the streets of those giant galaxies. We will never feel the heat of those newly born stars on our skin. We are like a prisoner, watching the waves hitting the shore, but who can never sail into the ocean. This is the most tragic reality of cosmic loneliness. Distances separate us not just in space, but in fate. But exactly within this crushing feeling of smallness, the most miraculous truth of being human shines. Because, yes, we are physically small, but our mind is big enough to grasp the universe 93 billion light-years in diameter. The only being that can imagine those trillions of galaxies, understand how they were formed, and solve their chemical structure is that 1.5 kilograms brain inside this small body. We cannot go to the universe, but the universe can come to us. A photon starting its journey from that most distant galaxy reaches exactly your pupil at the end of its 13.4 billion year journey. And at that moment, you become the universe itself. You too, at some point in your life, might have felt lost, small, and insignificant in this massive world. But remember that the smallness you feel is also your greatest strength, because you are one of those rare and precious moments when this massive universe becomes aware of its own existence. You are the consciousness that answers the questions the universe asks itself. The second and perhaps more personal contrast is about time. Infinity and transience. On one side, as Webb proved to us, there is a universe that has existed for 13.8 billion years, will continue to exist for billions, or even trillions more, and seems almost eternal. On the other side, our lives stand, which average 80 years and last less than a blink on the cosmic calendar. On the universe's infinite timeline, our existence is as if it almost never happened. We are born, we love, we learn, we struggle, and then we vanish. Our story is not even a single letter in a giant library. This reality adds a tragic urgency to our existence, because our time is very limited. While there are trillions of worlds to discover, we only have the chance to experience one, and even that, only partially. While there is infinite information to learn, our memory and life are limited. This is like starting a book we can never finish. This situation could make all our efforts meaningless. If everything will eventually be forgotten, if cosmic time will erase us all, then what importance do the things we do today have? But this transience is also the very thing that makes life valuable. Because, for something to be meaningful, it does not need to last forever. In fact, on the contrary, being finite makes it priceless. The beauty of a flower comes from knowing it will wither. The value of a moment comes from knowing it will never come back. We live in the luckiest period of the universe. In that golden age when all the lights have not yet gone out, when galaxies can still be seen, no. And the universe is still young and alive. We are the witnesses of this short moment. You too face the transience of your own life every day. The people you lose, the memories you leave behind, and the uncertain future ahead of you. But this transience does not have to drag you into despair. On the contrary, this is an invitation to live every moment you have more fully. Because the love you feel right now, the dream you have right now, and the curiosity you feel right now is a unique and unrepeatable event in the 13.8 billion year history of the universe. Our meaning is not to leave a mark in infinity, but to do justice to this short glow. The third and most existential contrast is loneliness and togetherness. Webb's images present a universe view that is eerily lonely, with gaps of millions of light years between galaxies. Each galaxy is like an isolated island, drifting in a dark ocean. Even if there are other life forms, there are massive distances and physical laws that prevent us from communicating with them. This is the deepest and saddest interpretation of the Fermi paradox. If the universe is this big and this old, why is everywhere so quiet? Perhaps we really are alone. Perhaps in this giant universe, we are the only example of conscious life. This thought places a terrible responsibility on our shoulders. We might be the only beings carrying the meaning of the entire universe. This is an unbearable feeling of loneliness. Like having billions of siblings, but never being able to know any of them. This might be the most ruthless joke the universe offers us. A universe full of potential, but a potential that cannot be experienced. But again, with that word but, another reality shines within this dark picture. Because, yes, we might be alone on a galactic scale, but on an atomic scale, we are all connected to each other. The carbon atoms that make you were forged in the heart of a star billions of years ago. The oxygen you breathe was scattered into space by the supernova explosion of another star. The water molecules in your body were perhaps once part of a comet. You are a being made of stardust. Your body is a living record of the history of the universe. This is not just a poetic expression. It is a scientific fact. And this fact connects you not just to the stars, but also to every living thing on Earth. That carbon atom in that tree and the carbon atom in your body are siblings. The water in that ocean and the water in your blood are relatives. You are not an isolated piece of the universe. You are the universe itself. You are a piece of the cosmic web. You too might sometimes feel completely alone in this crowded world. But remember that even in the deepest moment of loneliness, you carry a universe within you, consisting of trillions of atoms. And each of those atoms connects you to this great cosmic family. Therefore, our loneliness is not an absence, but moments when we forget that we are part of a whole. These contrasts, yet big and small, infinite and temporary, alone and together, are only the first pieces of the intellectual puzzle Webb offers us. But this philosophical journey does not end here, because the telescope's mirror does not just show us these contradictions. It also offers clues on how we can find meaning in the midst of these contradictions. And these clues lead us to perhaps the most challenging, but most enlightening thoughts. These are thoughts about the nature of meaning, purpose, and the ultimate end. And these clues lead us to the fourth and most existential stop of our journey, the meaning of the end contrast. On one side, there is that inevitable, cold, and ultimate end, to which Webb indirectly points. The expansive effect of dark energy shows that the universe is not a paradise that will live forever, but that it is heading toward a big freeze scenario, where lights will go out one by one, and only an infinite darkness will remain. On the other side, there is our insatiable desire to explore, create, and seek meaning, despite knowing this end. This contrast, at first glance, can create a terrifying nihilism that makes everything meaningless. Because if trillions of galaxies, billions of years of history, and countless civilizations will eventually vanish, what meaning can a piece of music we compose, a poem we write, or a discovery we make with Webb have? If the universe will eventually erase all its memories, are our efforts to be remembered in vain? This thought is the heaviest emotional burden that the cosmic scale places on us. Because we are beings who want stories to end with a happy ending. But the universe does not promise us an end. It promises us an extinction. But exactly within this despair, the brightest and most provocative truth of being human shines. Because meaning is measured not by how long something lasts, but by how intensely it is lived during that time. A song does not need to play forever to be beautiful. In fact, if it played forever, it would lose its beauty. The fact that the universe is finite does not make our existence today worthless. On the contrary, it makes it unique and unrepeatable. We live in that golden age of the universe, when it is still warm, still bright, and still alive. We are those rare eyes, opened so that the universe can see its own beauty, before the light of the galaxies goes out. You too. If you wake up every morning and look at the sun, despite the difficulties, losses, and that inevitable end in your life, then you are a part of that cosmic resistance. Even if the end of the universe is approaching, the love you feel right now, the dream you have right now, and the curiosity you feel right now are real. These feelings are a rebellion against the cold physical laws of the universe. Our meaning is not to leave a mark in infinity, but to do justice to this short glow. The fifth and final contrast is perhaps the most paradoxical one: the wisdom of ignorance. Before the Webb telescope was launched, we thought we understood the universe, that we had solved most of the big questions, and only details remained. Our models were solid. Our equations were elegant. However, every single piece of data Webb sent, instead of confirming what we thought we knew, destroyed it. On one hand, we have the greatest accumulation of knowledge and the most advanced technology in human history. On the other hand, there is this massive, dark ocean hitting our faces, and the fact of how little we actually know about the universe. This situation might look like a scientific defeat. Every discovery we make produces many more questions than answers. How did the first galaxies form? What is dark matter? Why is the universe expanding so fast? It is as if the more we learn, the more the boundaries of our ignorance expand. This could cause us to feel that the human can never fully understand the universe, that our mind is insufficient to solve this cosmic puzzle. Science might look not like a path to absolute truth, but like an infinite labyrinth, where we move by fumbling in the mist. But this state of not knowing is actually the greatest engine of science and the human mind. Because if we knew everything, our curiosity would die. There would be no new continents to discover, no new mysteries to solve. These new questions Webb offers us are actually the greatest gift given to us, Cherokee. They herald that the adventure is not over, that the universe is full of surprises that will amaze us, and that our learning journey is infinite. Not knowing is not scary. Not knowing is the freedom to explore. Our ignorance is the measure of our potential. You too might be struggling with unanswered questions, uncertainties, and unknowns in your own life. But remember that what defines you is not what you know, but what you are trying to learn. Just as Webb looks at those blurry, love-fought distant galaxies and tries to give them a meaning, you too look at that blurry silhouette of your own future and create a meaning. This uncertainty is what makes life worth living. If you knew exactly what would happen tomorrow, today would have no excitement. We are beings in love with the mysteries of the universe. And Webb proved that this love will never end, because the universe will always be one step ahead of us. In the middle of all of these contradictions, these paradoxes, and this massive void, what are you, who are watching this video right now, feeling? Perhaps a strange feeling of emptiness, a smallness, as if you are being crushed under the weight of those trillions of galaxies. Or maybe exactly the opposite, a feeling of expansion, freedom, and greatness that is hard to describe, with the power of knowing that you are made of the same matter as those stars. Perhaps you feel both lost and found, both insignificant and priceless. And do you know what? Both feelings are correct. Because being human is walking on exactly that thin line between these two abysses. We are both dust and God. Chitaut, we are both temporary and infinite. We are both alone and a whole. The Webb telescope showed us not just the universe outside of us, but also that complex, contradictory, and massive universe inside of us. The dizziness you feel while looking at that mirror is actually the dizziness of your own potential. Now, we know that the journey is not just into the depths of space, but also a journey into the depths of our own existence. The James Webb Space Telescope. Every time it opens its metallic shutters and looks into that cold darkness, is actually opening our eyes. It says to us, look, here is your home, here is your past, and here is your future. Those impossible galaxies, those giant black holes, and those life-filled moons, all are part of your story. And we are not just the readers of this story, but also its writers. Our journey does not end at the end of this video. On the contrary, it starts anew with every new piece of data, with every new discovery of Webb. The doors of the universe have been opened wide, and the light leaking from there will continue to enlighten our minds. Our duty is to follow that light, to never stop asking questions, and to make our own meaning shine within that infinite darkness. Because no matter how big, how old, and how mysterious the universe is, its greatest miracle is that small, fragile, but brave consciousness that can look at it and say, how beautiful. That is you. We witnessed the massive history of the universe of billions of years. It's never, but I haven't told you the real shock. In the middle of these trillions of galaxies, we see there is a terrifying silence. We call this the Fermi paradox. In our next journey, we will solve the mystery of this deafening silence and the great filter. Where is everyone? Are you ready to face our cosmic loneliness?